Broadband antennas have been developed to serve many different functions. Let's consider some of the requirements that must be met in the field of communications. The sounds we hear are contained within a frequency spectrum which is approximately 10,000 cycles wide. The amount of intelligence which we can convey is therefore related to the width of the spectrum. This simple 500 cycle tone can be represented mathematically by a sine wave. To this fundamental, we will now add the second harmonic. The change of sound is caused by the modification of the wave shape. A further change in the sound is caused by the addition of the third harmonic. The waveform has again been changed. Each increase in spectrum width increases the quality or intelligence conveyed by the sound. If we play a 500 cycle note on a saxophone, the harmonics create a distinctive wave shape. If the same note is played on a flute, we obtain a different harmonic pattern. Again, the wave shape shows that we must pass additional frequencies to retain musical quality. It is the harmonics which identify different musical notes. The human voice, which can be likened to a musical instrument, is best depicted on the larger spectrum.
1, 2, 3, 2, 1.
On an average, the frequency range is about 8,000 cycles. The associated wave shape looks like this.
1, 2, 3, 2, 1.
By filtering out inessential harmonics, we can reduce this range to 3,000 cycles.
1, 2, 3, 2, 1, 2, 3.
Since the intelligence has been retained, we have produced a voice channel. To understand how this information is transmitted, let's return to our 500 cycle waveform. To facilitate transmission, we frequency modulate a carrier wave. Here's what happens. When the waveform is positive, the carrier bunches together. This process produces a sum frequency. When the waveform swings negative, the carrier is expanded. This process produces a difference frequency. If we change the waveform to that of our speech channel, the resulting modulation will be more complex.
1, 2, 3, 2, 1.
Let's assume that our carrier has a frequency of 30 megacycles. The modulation process produces sum and difference frequencies.
1, 2, 3, 2, 1, 2.
This block represents one channel of information. In practice, it is desirable to widen this range so as to transmit and receive a number of channels of information. This requirement is not achieved with the simple dipole. This antenna has a high efficiency at a spot frequency. That is to say, a high Q. To increase its bandwidth, we must lower its Q. This process is known as broadbanding. Let us see how it is achieved. In the VHF region, we can fold the dipole or change the rods to current sheets. In the UHF region, the upper element can be replaced by a capacity hat and the lower element by a cone. This antenna has directivity and broadbanding, but has less gain than a simple dipole. The squirrel cage antenna overcomes this limitation. It is usually mounted as a vertical array. This antenna concentrates power and provides high gain as well as broadbanding. Let's return to our single voice channel and consider a further example of the need for broadbanding. It is often desirable to transmit many voice channels. The electronic compounding of all these voice channels produces a baseband signal which may be many kilocycles wide. To transmit this baseband, we might use a carrier of 600 megacycles. Again, sum and difference frequencies are obtained. Each block represents a carrier being modulated by many voice channels. Broadbanding in this region enables us to handle a number of carrier frequencies. As before, we must lower the antenna's Q to achieve this broadband requirement. Broadbanding in the microwave region is easier to achieve. Because of the smaller wavelength, our dipole is physically smaller. And we can lower its Q by increasing its rod diameter. In this form, the antenna is very inefficient because it affords a very small capture area for reception. By adding a reflector, we can restore our high-gain broadband requirement. Some installations use flared horn and lens systems. Others use large, high-gain dishes. All these antennas have a greater bandwidth and higher gain than those used in older HF systems. Broadbanding thus permits greatly improved methods of communication with increased flexibility. The line-of-sight system gives high traffic capacity over short distances. Range can be greatly increased with the tropospheric scatter system. In this system, the beam is directed at the horizon. Its energy is then re-radiated by the millions of particles in the atmosphere. This re-radiated energy is picked up by high-gain dishes. Even greater range is possible with the ionospheric scatter system. A powerful beam is directed at the ionosphere. Reflection occurs, and the reflected energy is then picked up in the target area. To achieve these greater ranges, we must accept some loss of traffic capacity, but with communication systems like this, we can span the globe. Even the faint radio signals from outer space can be picked up with super high gain reception equipment. While the tracking of satellites is achieved with great accuracy. Antenna design and performance will be a vital element in the development of equipment for the space age.